right. Practice exam. Draw the beta hydrogen molecule. How many types are there? So for this, you need to find the carbon that's attached to the leaving group. And beta hydrogens are 2 bonds away, 2 bonds away, 2 bonds away. And so there's 3 different types. And so the reason I know there's different types is because this molecule is not symmetrical. If it was symmetrical, they'd be the same. So there's 3 different types, so they lead to 3 different alkenes. Next question, I ask you to form the Zaitsev product, so you gotta remember what Zaitsev means. That's the one that's the most substituted alkene possible, right? So tetrasubstitute would be the most. And for an E1 reaction, so you gotta remember what an E1 is. Other things you can look for, so I told you it's an E1, so you should just remember what E1 means. It means you're gonna form a carbocation, so if it's a chlorine, a bromine, or iodine, the leaving group just leaves. Right, notice we have a polar protic solvent. We're going to make a carbocation. It's a tertiary carbocation, so we can't make it any more stable. We don't need to do a rearrangement because in case you try to do a rearrangement, if this H moved for a rearrangement, you make another tertiary carbocation, which is just as stable. So there's no reason to do that. So it just does an elimination. So beta proton transfer elimination step. It makes the tetrasubstituted alkene, which is more stable according to Zaitsev's rule. And then you get the H plus is falling off in the CO. I wasn't recording. E2 reaction, leaving group must be axial. Right, so in this case it's equatorial, I need to flip it. All right, leaving group must be axial, it doesn't matter if it's up or down. So this is axial up. So once I do the ring flip to get the leaving group in the right spot, I need to look for beta hydrogens that are also axial, but on the opposite side. So if this is axial up, I need to look for beta hydrogens that are axial down. So there's 2. There's one on carbon 6 and one on carbon 2. And the reason I chose the one on 6 is because it leads to the more substituted alkene. This is a tri-substituted alkene. 2 would lead to a di-substituted one, so it's less substituted. Another Zaitsev's rule type thing. More substituted, the better. E2 reaction has 3 arrows in one step, right? The base, bulky reactive base, grabs the H. Those 2 electrons make the pi bond, goes between the 2 atoms, and the leaving group leaves. So 3 arrows, 1 step, that's that E2 reaction. And you could draw it, if you want to draw it like this, that's fine. You can draw it like this. Biggest thing I saw, people weren't numbering, they're losing carbons, or they're adding carbons, right? Make sure it helps to number them out sometimes. This one, so asking for mechanism and resonance arrows, so these are just those curved arrows. So the first step, pi bond reacts, right? Breaks the OH, right? Make sure you show the OH bond breaking too. Make a carbocation. The ring expands. Why would it do that? So a three-membered ring, right, is like a triangle. So their bond angles are 60 degrees. The hybridization state of all these carbons is sp3 hybridized, so their bond angles are 109.5, so it's a pretty strained ring. So a 3-membered ring is not very good. It's pretty strained. So it pops open. So it goes from secondary to secondary, but again, now we're stuck with a square. So these have bond angles of 90, so it's even worse. Or it's not worse, it's not great. So there's another hydride shift to get to a tertiary one. Doesn't another shift to get to a secondary that's not a plus charge in the ring, right? Because a plus charge in the ring is even worse because the carbocations are sp2 hybridized. So bond angles are 120. Again, I'm not asking you this here. I'm just asking you to show the arrows move. Remember, you start arrows, never start an arrow at a plus charge. Hydride shift, ring opens again, 4-membered ring to a 5-membered ring. Secondary carbocation. We'll then do we'll do another, I didn't draw it in here, I guess I forgot to, my fault. We have another H shift, right, to get a tertiary carbocation. And then finally, right, we do the elimination, E1 elimination, and get the final product. So a lot of this was just mostly going around and making sure, right, you could do bonds broken, bonds formed. Numbering really helps here too. make sure you start your arrows at bonds and electrons in bonds, not at a plus charge. Alright, so for this one, mechanism arrows, wedges, and dashes. So Cl2 is just like Br2, so it's halogenation, but if you have protic solvent around, it becomes halohydrogenation, right? So this first step is the same for this and the oxymercuration. 3 arrows, pi bond reacts with the chlorine, breaks the chlorine-chlorine bond, lone pair in that front chlorine comes back. We make this 3-membered ring, right? Pi bond reacts. It's 3 arrows, one in addition, 1 step. A lot of people ask me, well, where do the wedges and dashes come from? Well, I just arbitrarily decide that these 2 bottom ones are going to be wedged, and these 2 are going to be top or dashed. Notice how I draw the H's in on the alkene. Should do that. And I do this because now I don't have to worry about changing my wedges and dashes as I do this. It's just set, right? So it's like the chlorine came to the top, right? It could have also come to the bottom. If you draw it that way, that's okay. The difference here is because we have a protic solvents react. So if you see protic solvent, it's got to react. If there was no solvent here, then the chlorine would add. But there's protic solvent, right? And plus you also saw the product. Hopefully you see that there's a oxygen added. Oxygen lone pair adds to the more substituted carbon, right? That's that SN2 breaks that bond, right? Make sure you're balancing your charges all along the way here. SN2, gotta draw the arrows in the right direction. Oxygen sells a plus charge, right? Nothing happened to this carbon, nothing happened to this hydrogen. We do a proton transfer, the hydrogen falls off, right? So we get H plus and a Cl minus, same as this. And I drew in the wedges and dashes here, just like I had here, but I just had to draw them in. You're done. So this one's about hydroboration and oxidation. And this is an example of, okay, there's the ring, and right, you could flip it over, but the way I have it drawn, basically what I'm looking for is 2 parts. So you recognize hydroboration means the H goes to the more substituted carbon of the pi bond, which is different than all the other ones. And that the H and the boron, remember they had 2 arrows in 1 step. They have that syn addition. So the boron and the H need to be on the same side, and the H needs to be on the more substituted carbon. The boron's on the less substituted, so that's why this is the right answer. But right, this is what I was talking about. These are a little harder. Right, we could do a lot of brain work here, but H more substituted carbon, boron less, and on the H and the boron on the same side. So if we were to draw this out, and just because this is a ring, I drew it this way to help me see it. Pi bond reacts, H goes there, and it's all the same time, and that leads you to that. All right, so I just took the ring and kind of flipped it, and then 2 arrows, 1 step, that's syn addition. And so here's the boron coming from the bottom, H is up, okay, there you go. 2 arrows, 1 step, syn addition, syn product. So give the mechanism of the products. This is the acid catalyzed solvent addition. People got kind of thrown off, right? H3O plus is just like H plus in water. I gave you the steps, so make sure there should only be 3 steps. So don't do more than that, and don't try to combine these steps, right? Always check yourself, balance your charges, slow down. Pi bond reacts, takes the H. Make sure you break the OH bond. We make the carbocation. The H goes to the less substituted carbon, right? We draw the H's in the alkene, so the H goes to less substituted. We get a tertiary carbocation. I can't get any better than that. Yeah, I could. This could do an H shift, but that gets me to another tertiary. It's not better, so we stay put. Plus, I didn't tell you to do that. Addition, the only thing left to add is the solvent, right? So so the solvent adds. Make sure you keep the H's on there. Deprotonate, right? So we get the alcohol. And then, of course, we ask ourselves our last question is, did we make a chiral center? Right? Do we have something that's sp3 hybridized bond to 4 different things? And we do. So we got to draw both versions. So the way I did it, one way to do it, was draw the methyl wedge, OH dashed, and then the other enantiomer, keeping everything else the same, and just switching those 2 around. So you draw, that's the other enantiomer you could draw up. So this one's actually the same as the one above. It's an acid catalyzed solvent addition. Just looks a little different. It's H plus, maybe you're more used to. And then protic solvent. First step, pi bond reacts. Right? Add the H to the less substituted carbon. Get a carbocation. We're going to do a rearrangement. One of the ways I knew we had to do a rearrangement was because if you had numbered these carbons, as you should have, which I didn't, you would notice, of course our H's are on there too. Right. You would notice that the sulfur doesn't add to carbon 2. It tells you it has to be a rearrangement, right? That something had to move. So an H had to rearrange. So it went from secondary to secondary, but this is secondary benzylic, which is more stable, right? Now the solvent adds deprotonate, make sure the electrons go to the sulfur. Hydrogen never takes the electrons. And the last step, of course, is proton transfer, regenerating that catalyst. So for this one, this is that oxymercuration, demercuration. So this is just like halogenation and halohydrogenation. So that first step is 3 arrows addition. So just treat the mercury, right? Like it was like right? This other acetates along for the ride. So pi bond adds to mercury. You break the OAC bond. These are just OACs. O-acetates, same thing. Mercury has a lone pair, it goes back there. Makes that 3-membered ring. And I know some people have some really good questions about the octet rule. Like mercury's weird, it doesn't follow it. That's why I wanted to show it to you second. And I showed you the BR2 first. But this is just like that, right? 3 arrows, addition, 1 step. Again, I drew the H's in on my alkene. That helps. I put the 2 groups down as wedged, 2 groups up as dashed. Mercury, if there's a protic solvent, that's what's going to add. That's the other thing it's going to add, some protic solvent. Lone pair adds to the more substituted carbon. SN2 style, right? SN2 style. And again, don't forget, I gave you some hints up here, right? So if I give you these hints, these are the things to look for, right? Don't make it harder than it has to be. Like a lot of times I saw some folks like forgetting to look at the product or forgetting these steps, right? And trying to do it without those things, right? Don't make it hard. Don't use the resources you have in front of you, right? If I tell you it's need to, make sure you do need to, right? Those kind of things. So make sure you slow down and read those instructions. Are there clues or hints I give you? Solvent adds to the more substituted carbon, SN2 style. All right, solvent adds. Notice the product, these things are trans to each other. It's that anti-trans thing. Deprotonation. You got that H plus. Right, and I know Achieve did this really well. Showed the mercury, right? The lone pair came back to the mercury when that bond broke. These 2 things are trans to each other, right? Step 4 is just the magic step where mercury becomes, oops, I didn't put the product in, my bad. Where mercury becomes an H, whoops. Let's see what that product looks like, shall we? And now we ask ourselves, did we make a chiral center? I think we did. This is bound to 4 different things, sp3 hybrids, so I could either write plus an antimer, or if Wenzel's being aggressive, he wants you to draw it out. What would we do? Just put that there. Don't need to change the wedges and dashes, just need to flip things around. And there's the enantiomer right there with it. Nice.